Today I'll continue the discussion on optical spectra, which is obtained from semiconductor lasers. Last time what I discussed was how from the optical absorption spectra one could derive the photoluminescence spectra on the basis of certain models. Today I'll go to a little more advanced models, and then I'll talk about the matrix element, how the matrix element is calculated. Overall, the subject of today's talk is gain in semiconductor lasers. And in the discussion of the threshold current density, obviously the losses must be offset by the gain. Okay, so there was a relation G is equal to alpha plus 1 by L log 1 by R1 R2. Okay, so we want to calculate this gain in a semiconductor laser, and gain comes from stimulated emission. So we can define a gain coefficient like this, that the intensity Ix after traversing a distance x is I0 e to the power gx. Okay, so G, the gain at a particular energy, is just equal to minus alpha is equal to N2 minus N1 B12 over C by N bar. Okay, that's the velocity of photons in the medium. We had derived that last time. We had derived this expression last time. And G is, if you look at the definition, it is the power emitted per unit volume over power crossing per unit area. And one can write this as GE R stimulated emission over C by N bar NE. This is in centimeter inverse, the same units as absorption, where this is the photon mode density, the number of photon modes, and UE is the average number of photons per mode, which obeys Bose-Einstein statistics. From this one can get to the expression that which I derived for alpha, so this is just minus alpha, is 2 pi q squared h cross by 3 n bar c0 m0 squared c integral over k space, this matrix element squared, which will the momentum matrix element squared for transitions from the conduction band to the valence band, downward transition, so F2 minus F1, and delta E2 minus E1. This is conservation of energy rule, okay, minus H cross. Okay. So last time we discussed that the final this gain term will depend upon this value of the matrix element and the density of states. We can also write this in an equivalent fashion using, this is where we use Van Roosbroek-Shockley relation. We can write G of E is related to alpha of E. This is equal to 8 pi n bar squared E squared alpha E over h cubed C squared, and the Bose-Einstein formula, e to the power kt minus 1. Okay. So here we see that I think there should be a minus. This is GE is related to alpha E. Okay. So what we have to discuss are the density of states. Remember, last time what I discussed was there are various models of the density of states. From we had the density of states. We had the first parabolic band, then the Kane band-tail model, then there was a Halperin-Lax density of states, and finally there was the Gaussian. It's a combination of Kane band-tail and Halperin-Lax, Gaussian Halperin-Lax band-tail model, GHL BT, and the proposers of these models, this is Lasher and Stern in 1964. This is Stern. This is immediately after the invention of the laser, the people Wang in 1970 and in Stern in 71. So this is, all these are rather old, but it's essential to understand that a lot of work has been done, and a mathematical agreement between theory and experiment has been obtained using certain models. For example, the simplest model, the parabolic band, if it agreed with the experiment, fine, then that would have been the end of the story. But physically, we are talking about highly doped materials, so heavy doping effects are coming in, band tailing is coming in. So in order to get agreement between theory and experiment, one has to introduce certain refinements into the band model. Okay. I'll be talking about the different types of matrix elements that are assumed. First, there's a constant meaning energy independent matrix element that was assumed. Then there were energy dependent matrix elements, and finally there was Stern's modified. So these went hand in hand with the new density of states, and ultimately reasonably a good agreement was achieved between theory and experiment. So first we take this Lasher and Stern. We have constant matrix element, okay, energy independent, to calculate the gain coefficients. But it did not give very good results. And then we went to the energy dependent matrix elements, in which M was taken to be a combination of a block function and an M envelope function. So in this case, what they assumed was they were trying to look at the transition probability between an acceptor and the conduction band. Okay. So a localized transition, and it was found that one could calculate this. I am just giving the outline, but obviously that mv squared, the the block states for these impurities, Mb squared could be written as M0 squared Eg plus delta over 12 mH Eg plus 2/3 delta. This is for 3,5 compound, okay, for direct gap. Where M0 is free electron effective mass, free electron mass. This is the okay. This is Mn. Sorry, this is Mn. So Mn is 0.067 M0, free electron mass in gallium arsenide. What is delta? Yeah, spin orbit splitting. Okay, so that is 0.33 eV for gallium arsenide. And Eg is the band gap of gallium arsenide. And one can write this as Mb squared is 1.33, simplified as 1.33 M0 by Eg. And the other component, the envelope function, is given by, dependent upon the effective Bohr radius, that is given by 64 pi A star cubed 1 plus A star squared KB squared to the power minus 4, where A star is 4 pi epsilon h squared by M star Q squared, is the effective Bohr radius of the localized state. And KB is the corresponding wave vector twice, say, MC EC dashed by h squared k squared is equal to, h squared k squared by 2 is equal to, by 2m is equal to EC dash. So, okay, this is the corresponding wave vector, where EC dashed is measured from the conduction band edge, and combining MB and M envelope, one finds that the total matrix element is 1.33 M0 EG into 64 pi So notice that KB occurs in this is divided by KB. So for higher value, higher photon energies, okay, this K is a small value, and this is where we have, there's no K selection rule. This K conservation breaks down because of heavy doping. Okay, so this is one of the main differences between the usual optical transitions and this. Okay, so especially at lower energies. Okay. So this is called the Stern's modified matrix element. If I SME, Stern's modified matrix element, and one can actually calculate this. And finally, the objective is to get numerical agreement between experiment and theory, and so one compares the more advanced calculations, alpha against E, and there here we will, this is absorption and this is PL, okay, intensity versus emission intensity versus E. T equal to 297 for both. P0 is 1.2 10 to the power 18, so realistic materials, really heavily doped. And if we, okay, this is 10 to the power 5, this is 10 to the power 1, fairly heavy doping. And if you look at the, okay, let's first plot the experimental data. Experimental data, as we saw, was not as sharp as the parabolic band. That was, okay, the experimental data is something like that, that is experiment. Okay. And if you take the most advanced modeled GHL, BT, SME, okay, you find that there's some difference. There is not, okay, this is all the GHL, BT, SME model. And there is certain amount of divergence. Even here, where it saturates, there is a little bit of difference. So in order to overcome this difference, numerically, what people did is that they thought that there is some underestimate. If you multiply this by 1.6, okay, it can make, you get a curve which is, okay, so this is GHL, BT, SME multiplied by 1.6. Okay, so that is giving you better results. I'll show why a factor of something like 1.2 may occur. It turns out that Dean had pointed out that if you take the contributions of higher bands in the matrix element, not only the lowest band, but if the higher band contributions are taken into account, then this SMA will be multiplied by a factor of 1.2. Okay. So there is some sort of rudimentary justification of but you see there is significant differences. But however, the nature of the curve is much better than we saw for the parabolic band. The parabolic band was something like that, like this. Okay, it's quite different. Now, if you look at the photoluminescence, then using Van Rosbeek-Shockley, what is the experimental data? The experimental data is something like calculation from experiment. The big tail at high energies, and these energies are unknown, 1.35 going to 1.55. Okay, and if that is the experiment, and if you calculate from the model using Van Rosbeek-Shockley, then you get, obviously there is, the same sort of discrepancy will occur. You will get something like slightly difference in the peak. So this is of some significance. Okay, and then overall you get merger. Okay, so these are experiments, and this is from the model. This is important because if you're trying to predict what is the spectral width of a laser, what is the nature of the, where does the peak occur, okay, what is the width, then obviously this sort of modeling is quite important. for example, there is really quite a lot of data on this. Suppose you take, in tabular form, suppose you take semiconductor, p-type semiconductor with gallium arsenide. Okay. Let's see how good the agreement between theory and experiment is as far as peak position and half width. Okay. So suppose you take heavily doped materials, 1.2 10 to the power 18, 2.4, 1.6 10 to the power 19, so heavily doped. Okay. Looking at PL, okay. What is the peak energy and the half width, both in electron volts. Okay. Experimentally, this turns out this is 1.415, this is 1.415, 1.400. Okay. This is 0.59, so 59 milli-electron volts, 0.61, little broadening due to heavy doping. Now suppose we do calculations from alpha. The peak position then will be 1.425, 1.420, 1.405. Okay. So exact values do not match, but there is the same trend. This is decreasing. And if you do calculation from model, from theory, then this is 1.414, 1.411, 1.398. Okay. So again, this exact values do not match. There is a difference of about 10 MeV, but the same trend. What about the half width? Calculation from alpha, you get 63 MeV. This is an MeV. Okay. 65, 73. Okay. And from model, these are 63, 64, 74. Okay. So now here you see there's pretty good agreement between the full width half maximum from calculation from alpha and the model. So now at least one can say that, okay, one understands what are the main contributions to the energy and the half width. And from this data, for example, one can show that in gallium arsenide, the band gap due to heavy doping is given by a relatively simple relation, 1.424 minus 1.6 into 10 to the power minus 8 P0 to the power 1/3. Okay. This is band gap narrowing. You can see P0 is the density, okay, total density, and P0 to the power 1/3 is approximately the distance between the average distance between the acceptors, etc. So this is sort of theory of band gap narrowing. Okay. Now, having satisfied ourselves that we can we have some idea of the spectra, let us go to calculation of the gain using those relations. And for gain, the input is obviously the carrier concentration. Suppose we have a material which is in thermal equilibrium. There are some, suppose we plot alpha here and G here. This is 0 and this is energy. Okay. Okay, if the material does not have any injected carriers, it will be passive, there will be some absorption, and the absorption spectra will be given by say something like that. Okay. Near, this is 1.35 eV. Okay. Now if you you start injecting carriers, okay, this curve will shift a little bit, and then when you are injecting, this is, okay, for P0 is 1.2 10 to the power 18, where heavy doping effects are coming in, and T is 297. As you start injecting carriers, then you start getting a little gain, followed by absorption. Okay, you start getting and then thereafter you get, okay, the gain will peak, and you will get spectra like that. And say here is 1.45 eV. So what is important in lasers is the energy at which this peak occurs, maximum gain. Okay, the laser will tend to oscillate at that energy, and what is the magnitude of the gain. If the magnitude of the gain is very large, it will overcome the losses, and the threshold current will be. If we look at this area in a little more detail, we find that
different current due to different current.
Yeah, different currents. I'm just giving you values. This is GE centimeter inverse, and just this part, if you blow up, then you find that you get curves like this. Okay. This is 1.44. Instead of currents here, what we are just considering is that the current is giving you some injected current density. Okay, here it's 1, 1.2, 1.4, 1.6, 2 into 10 to the power 18. This is, you can say this is delta P. Okay, and delta P is equal to delta N. So the Fermi level splits, and so with this excessive, this delta P and delta N is obviously due to current J. The gain increases, and if the gain is enough to overcome the losses. Okay. So using this sort of these curves, these calculations, one can now go and use the relation between we know that G is equal to some constant J minus J nominal, okay, in the linear region. So from this one can now calculate. These calculations were done just taking into account some injected carriers. Now if we this gain is due to injected current, then how does, and G max that I'm plotting here, G max is these values, okay, these values. This is G max, the peak of the gain curve. Okay. So how does that vary with I'm sorry, I think this should be, this is J norm minus that J0, you know, that J0 minus J0. Okay. This is amperes, centimeter squared, micron. And again, there are experiments and various models. Okay, what are the parameters here? Na is equal to 4 10 to the power 18. and D is equal to 1/10⁻18. Okay, and if you look at the various models, for example, the parabolic model will give you okay, let me put the axes. This is 10, 10⁻², 10⁻³ 10⁻⁴, 10⁻⁵. Okay. The parabolic band tail model gives you some values like this. That is at 160, and that is at 300K. The gain band tail model gives you something quite different. It gives you like that, and so this is gain. This is parabolic. And the most realistic HLBT model gives you something like this. Gives you, let's see, okay. And something like this. Okay. This is the HLBT model. So you see, because the gain versus energy curves are different, each of these models gives you different predictions as to gain maximum versus J norm. And how do you know which is good? Well, you have to test with experiment. If you now plot G max centimeter inverse against the same thing, against J norm, smaller region, 10⁻³ to 10⁻⁵. Okay. The ordinary GHLBT model gives you something like this. Sorry, this is the Halperin-Lax band tail model. Okay, HLBT. Important thing is the experiment. What are the experimental points? The experimental points go something where the gain goes from 10 to 10⁻³ centimeter inverse, and it turns out that with some fitting, the this is the GHLBT SME model, okay, with band gap shrinkage. So you see, again, there's once you have something as close as this, then you can see that there is some reasonable agreement between experiment and theory. So the object of this discussion is not to take you through all the detailed derivations, but at least to make you aware of what are the main assumptions, how you can gradually get agreement between theory and experiment, and how complex it is. It's simple. I've not gone into 2 dimensions. I've not gone into strain layer or anything. But it's a simple heavily doped gallium arsenide. To get agreement between experiment and theory, you have to make a lot of very important, drastic assumptions. So since we're talking about the spectral, let me just end with a discussion of line shape function and line width. I just mentioned what are the line widths that are available. If we plot the intensity versus, so either it can be, okay, this is nu, okay, so this is nu 0 and this is delta nu. So as in the case of any laser, we want to know what are the parameters that determine this line width, and the line shape function that we define here as S. S is defined as S nu d nu integral minus infinity to plus infinity is equal to 1. And as you can quite imagine that there are two broadening mechanisms in general, homogeneous and inhomogeneous. Homogeneous broadening gives you a Lorentzian line shape function, and this is essentially due to interaction with phonons. Remember, in gas lasers, etc., you get there are molecules. You get things like Doppler broadening, etc. Okay, here it is due to phonon interactions, and the phonons are generally of two types: acoustic and optical. Depends upon the phonon densities. Now, the acoustical phonon density increases with temperature. Is proportional to temperature, whereas the optical phonon density is relatively independent of temperature. This obeys Bose-Einstein statistics. So we can say that the homogeneous broadening delta nu homo is equal to, has two components, due to, one is due to acoustic, and which is proportional to temperature, and other part which is due to optical phonons, H cross omega L0. This is the optical phonon energy, KBT minus 1. Okay. And this is due to optical phonon. And okay, this xi optical is a optical phonon broadening constant. Okay. And it turns out that this term is negligible. So it is mainly the optical phonon term that dominates. Of course, this optical phonon energy is of the order of, we know what it is for each semiconductor. It's of the order of 40, 50 MeV.
At high temperature?
This is changing with temperature, right? But the optical phonon energies are relatively independent of temperature. And in order to get really, these are fundamental properties of the material, okay? I mean, there's nothing much you can do, but what distinguishes a good material from a bad material, we often look at PL, look at the line width, and we say that, okay, this material is very good, okay? And the line width is small. The line width being small means that material is good. What does that mean? Because it is the inhomogeneous component which is giving sample-to-sample variation. So variation of the electronic properties, okay, gives you inhomogeneous line width broadening. So, for example, if there is a localized strain, okay, if there is a compositional variation, say in gallium aluminum arsenide, the aluminum concentration varies from point to point, okay? Or if there's doping concentration variation. Or if there's, one of the most important things is alloy clustering, okay? The gallium aluminum distribution, it's not uniform. And of course there is things like interface roughness, especially in quantum wells, etc. So all these give rise to broadening. And of this, the impurity, this is temperature dependent, because the temperature determines what is the number of ionized impurities, okay? And this inhomogeneous broadening gives you a Gaussian line shape, and the total gain GE is given by this line shape function comes in D dashed, where this S nu 0 is, nu 0 by delta nu. Okay. So we see that for the line shape there is a temperature dependent part, temperature independent part. There is a part which is sample dependent, and a part that is just dependent upon the inherent properties of the material. And obviously we want, if we want a laser, we want as narrow a line width as possible, and so we want to, during growth, we want to reduce this localized variation. So one of the ways of experimentally checking this is, for example, when we have a sample, okay, and we have a laser light, argon ion laser coming, and we are getting photoluminescence, okay, PL output. It is not enough just to get PL output, from one little region. So we have to scan. Okay, so this is called wafer mapping. That we should obtain photoluminescence from different spots on the wafer to see how uniform, spatial variation of nu 0 and delta nu, that has to be examined. So one is experimentally through PL. That will obviously tell you what composition. If there's a composition fluctuation, then the nu 0 will change. And the other is DC XRD, that's double crystal X-ray. That will tell us about strain. Okay. Lattice parameter changes from point to point. Okay. Then the X-ray diffraction pattern will change, and we have actually done this, and we have plotted the DC XRD. Here also we measure the intensity and the line width. Here also PL, we measure the intensity, nu 0 and delta nu. Okay. So experimentally these give us information about the quality of the layer.